that
Okay.
tries to keep you on track.
Okay. And
So,
let's see, we click on college algebra, right?
yep.
And launch course.
Yep.
And tests or lessons?
Go to lessons.
Lessons, okay.
And then hit the all option.
Where are we at?
If you go to quadratic equations, number 7, just scroll down a little bit.
Do?
All right.
7.3?
No, actually, let's look at 7.5 for a second.
Okay.
So I did this last night and ended up going through and certifying, correct? But I wanted to just talk to you about how to recognize whether Perla is narrow or wide.
Okay. Let's talk about that. I can probably clear that up real fast. If I have an equation y equal x squared, that's the most basic parabola.
Mm-hmm.
Looks like this. Okay?
Mm-hmm.
Now, if I told you y equal 2x squared, that means every point that's on the x squared is going to be twice as far away from the x-axis. In other words, if I have a point there, in red, it would be right there. And if I have a point here, in red, it would be up there. You see that?
Mm-hmm.
Well, if I draw that parabola, it makes it narrower. So
Okay.
when you have a leading coefficient that's greater than 1, it's a vertical stretch, is what it's called. It makes the thing skinnier. If my function was y equals 1/2 x squared, that makes it flatter. Why?
Okay.
Why? Because every point that would have been on the black curve is now half as close to the x-axis. And that's why the green curve is flatter than the black curve, and this is called a vertical shrink. Shrink flattens the parabola. Stretch makes it skinnier.
So anything that's greater than 1 then would be classified.
1 is the magic number. If this is greater than 1, it's a stretch, making it skinnier.
Yeah.
And I can't say if it's less than 1. If it's between 0 and 1, it makes it flatter. If it was -3, like that, well, that minus sign is a reflection, first of all, and the 3 is a stretch. So that would have the effect of doing something like that.
Yeah, yeah.
Okay? So it's not whether this number is less than 1 or not. It's whether it's between 0 and 1. If it's between 0 and 1, that has a flattening effect. If it's greater than 1, it has a stretching effect.
Okay.
Okay? Now, let's look at our problems here. Hold on a second. Let me get this set up right. So this first problem.
So this would be downward, right?
Correct. It's all based on whether that leading sign is a plus or a minus.
Yeah.
If it's a plus, it opens upward. If it's a minus, it opens downward. Furthermore, let's go through how you would graph this thing. Well, let's start with the parent function. Okay? That is y equal x squared. That's what it's called, the parent function. Okay? There are three things going on with this function. There's a minus sign there in front. There's a minus 3 inside the parentheses, and there's a plus 1 on the end. Let's take each one of them. What's the and you always do the reflections first. In other words, order doesn't really matter when you're doing these transformations, except you got to do reflections first. Whether it's a reflection over the x-axis or the y-axis does not matter, but you got to do the reflections first. So in a different color, I'm going to do the first action. That curve would be y equal minus x squared. With me?
Yep.
Now, in a different color than that, if I can get it to come up, I'm going to do the second adjustment or transformation. What's the effect of that minus 3? That's a horizontal shift.
Mm-hmm.
Which way? Is it to the right or to the left?
To the left.
It's actually to the right. It's opposite of the sign that's there. In other words, the standard is x minus h. So h here is positive 3. Positive means to the right. Okay. So in green, I'm going to draw this curve. I'm just doing one transformation at a time here. This one is y equal minus x minus 3 squared. You with me?
Yep.
Okay. Now we'll take the very last transformation, the plus 1, and I'll do it in red. Not red. It's a new color here. How about yellow? You're not going to be able to see yellow very well, but nonetheless I'll do it. What's that last plus 1 do?
Does it move it up one?
Yes, it's a vertical shift. So I'm going to take this bluish curve and move it up exactly 1. Oh man. Here when I think that having options of all these colors is great, you can't see the yellow. Can you see the yellow there?
Yeah, I can see it. It's fine.
That's the final curve. That curve is y equal minus, because it's been reflected, it's been horizontally shifted, and it's been vertically shifted up 1. So let's talk about these transformations, because these are kind of important. Let me go through all the various transformations that you can do. If this is our standard function, what's called the parent function, it's always a good idea to know what the parent functions look like. Mm-hmm. There's like 10 elementary functions. You've probably been exposed to 7 or 8 of them at this point.
I think they did 5.
Okay, this is one of them, y equals x squared. Okay. Now, in different colors, tell me what effect this would have. What's y equal 2x squared going to look like?
Well, you have another...
Would it be skinnier or flatter than my first curve?
Be skinnier.
Correct, by a factor of 2. Correct. Because every point on the red curve has to be twice as far away from the x-axis as every point on the black curve. Mm-hmm. Okay. Now in green, let's do a different kind of transformation. X plus 1 squared. What's that going to look like? I'm just doing these one at a time rather than in combination. I have found that discussing transformations works much better if you do them one at a time. You can combine them all just fine, but you need to know how to do one at a time. So what's the plus 1 do?
It moves it over 1.
Which way? Left or right?
Right.
It's actually left. In other words, here's the standard. Y equal x minus h.
Yeah.
Okay? So whatever h is, if h is a positive number, then it moves to the right. If h is a negative number, it moves to the left. Well, notice in this case, h is a negative 1. See why?
Well, there's a bit.
If I had x minus a negative 1, it would come out to be x plus 1.
Yeah.
So when I look at x plus 1, I know that h has to be minus 1, which means it has to move to the left.
Okay.
Okay. So the green curve is going to be, if this is at 1, then the green curve goes right there. Same shape as the black curve, incidentally.
Mm-hmm.
Not the same shape as the red, because I didn't put the 2 in front of it. But it's the same width as the black curve. Okay. Now, let's do one other transformation in brown. Let's do y equals x squared minus 2. What's the minus 2 do?
Makes it a positive then, right?
Well, hold on. No, this is a little different. In other words, this is definitely a negative number, and it's a vertical shift down 2.
Oh, yeah, okay, so it's going down.
So it goes down to minus 2, which is where the vertex is going to be.
Mm-hmm.
It's going to have the same shape as the black curve, only it's the black curve shifted down by 2 units. Is exactly what it is.
Okay.
Okay. And let's see, there's one other that's not a reflection. Let's do deep blue. And that would be y equals 2x quantity squared. Notice the difference here. In my first one, it was 2 times x squared. Well, that 2 was just a vertical stretch factor. But this, the 2x is inside the parenthesis. If it's inside the function, then it's a horizontal transformation. And horizontals work slightly different than verticals. When the number is greater than 1, it's a horizontal shrink. If the number is less than 1, it's a horizontal stretch. So if I were going to draw my blue up here, I'm basically looking at 4x squared, which is even tighter than my red. Notice that vertical shrinks are the same, vertical stretches are the same as horizontal shrinks. Can you see how the blue is skinnier than the red?
Yes.
Well, the red was 2x squared. The blue is 4x squared.
Mm-hmm.
So the blue should be skinnier than the red, merely because it's 4 instead of 2. But the fact of the matter is that the 2 is inside the function being squared, not outside, and that's what makes it skinnier. Okay?
Okay.
So these are your 4 transformations. that you really need to know how to deal with those. And there's only two other transformations. Let's talk about those before we even go forward. If this is my primary function, my parent function, there's only two other things you can do to this function. One is to put a negative sign in front. That acts as a vertical reflection. Same exact shape, it's just the curve is reflected over the x-axis. Okay, you with me?
Yes.
And there's only one last thing that can be done. And that is if the minus sign is inside the function, like that, and if it's inside the function, that's a reflection over the y-axis. That's a horizontal reflection. Notice that a horizontal reflection looks exactly the same as the original function, as it should. In other words, if I do this process, I get y equal positive x squared. Negative x times negative x is positive x squared. So this green function should look exactly like that function, even though I had a negative x inside the parentheses.
Okay.
And the only reason I did was I wanted to illustrate all 6 transformations. And that's all there are 6 transformations. And basically what that means is that no matter what kind of function I have, there's only 6 things I can do to it. Let's say I have the following function. Another basic function. Okay? Well, what can I do to that? I can put a negative sign in front. That's a reflection over the x-axis. I can put a negative sign inside the function. That's a reflection over the y-axis. I can put a multiplier in front. That's a vertical stretch. I can put a multiplier inside the function. That's a horizontal shrink. I can put a horizontal shift like that. Notice that everything that's horizontal is inside the function, everything that's vertical is outside the function. Well, this is inside the function. It's inside the parentheses. So I know that this x minus 1 cubed is a horizontal shift by 1 unit to the right. So whatever this curve looks like, this is going to look exactly the same, only it's going to be shifted to the right by 1 unit. And finally, there's only one last thing you can do, and that is a vertical shift. That would be taking our original curve and moving it up 4 units without changing its shape. So those are the 6 things you can do to any basic function. And that's it. There's nothing else that you can do. In other words, if they give you a function, let's say they give you a function that's been shifted, and been stretched, and been vertically shifted. In other words, I can combine them all. Well, what's this got going on? This 4 is a vertical stretch. This 2 is a horizontal shift to the right by 2 units. This minus 1 is a vertical shift down by 1 unit. That's it. The basic function is y equal x cubed. So if I were to graph y equal x cubed, it looks like that. Now if I apply all three things, well, the 2 moves it right by 2 units. The -1 brings it down by 1 unit. And the vertical stretch factor makes it skinnier by a factor of 4. So it looks like that. So anytime you see a function, the goal is to figure out what the parent function is and what transformations are in effect. In other words, I know that 4 is a transformation, I know this -2 is a transformation, and I know the -1 is a transformation. If I remove all of those, I'm back to my original parent function, which is y = x cubed. And that's the way you handle these transformations. Now, let's see if that's a good primer for these problems. Well, the only thing they want to know is whether it opens upwards or downwards. Well, that's...
Yeah, and then there's a series of questions.
Right. I guarantee you we're going to get to transformations. This is, well, what's the minus sign mean? That means it's a vertical reflection. It's vertical because it's outside the parentheses. It's not inside the parentheses. So since it's a vertical reflection, it opens downward. Okay, determine whether the graph is wider or narrower than this other function they give you. Wow, they're kind of giving you these in backwards order, but you can still figure them out. In other words, if I had this function that they gave us at the top, and I compared it with this function at below it, which one is going to be skinnier?
The top one.
Actually the bottom one, because of that 3. That 3 right there is a vertical stretch factor.
Okay.
Okay, let me just draw it. In other words, if I was drawing the apparent function, that's y = x squared, and all of a sudden somebody says, well, what does y = 3x squared look like? Makes it skinnier, right? So they've kind of tried to confuse us here by going in the opposite direction. In other words, notice that the bottom function has the multiplier of 3. The top function doesn't. So this 3 is a vertical stretch factor.
Okay.
That makes it skinnier. So determine whether the graph of the top equation is wider or narrower than the bottom one. Well, it's got to be wider, because this 3 in the bottom makes it skinnier. That makes the top wider.
Okay.
Normally they would give you these in the other way around. They would give you this bottom function, and they would say, what's the effect of the 3? And the 3 makes it skinnier. The leading 3. Okay? But in this question, they're saying, how does the top compare to the bottom? Well, that makes the bottom wider. Excuse me. It makes the top wider than the bottom. If the bottom is skinnier than the top, then the top is wider than the bottom. This is in Vertex Format. Let's talk about Vertex Format for a quadratic. y equals a times x minus h squared plus some d, we'll call it. Okay?
Mm-hmm.
Now, a, if it's greater than 1, vertical stretch factor. If it's between 0 and 1, vertical shrink factor. You with me?
Yep.
H, horizontal shift. It's inside the function. Everything that's inside the function is horizontal. And if h were like 3, if I had x minus 3, it would be a shift to the right of 3 units. D is a vertical shift. It's outside the function. Therefore, it's vertical. Well, what are they giving us here? They're giving us...
So would that be positive 3, negative 1?
Positive 3, it's a horizontal shift, 3 units to the right.
Mm-hmm.
And this plus 1 is a vertical shift up. Now, it's worth knowing that shifts do not change the shape of the curve, ever.
Mm-hmm.
Stretches and shrinks do, but shifts do not. And the only thing we got going on here is we've got a shift to the right of 3 units, we got a shift up of 1 unit, and we've got a reflection over the vertical axis, which is the x-axis. Okay, so we're going to take our standard parabola, and we're going to reflect it first. You always do reflections first, and it does matter the order you do these. The only order that matters is that you do all reflections first, both vertical and horizontal reflections. You do them first, and then you do everything else, and everything else doesn't matter. Okay, let me do something here, just so that I can write on this thing. So let me write the standard parabola. Okay? See? That's y equal x squared. That's the parent function. Well, this negative sign is just a reflection. So the first thing I'm going to do is that.
Mm-hmm.
Then the 3 is a horizontal shift to the right. So I'm going to move it so that the vertex is there. Still with me?
Mm-hmm.
And then the plus 1 moves everything up 1. So now the vertex is at that point right there. And let me draw it in a different color. Notice the shape has not changed. I have not widened it. I haven't stretched it. I haven't done anything to the shape. And the new vertex is right there. Well, the old vertex was at 0, 0, correct?
Mm-hmm.
Well, the new vertex has been shifted 3 units to the right and 1 unit up. Therefore, the new vertex is at 3, 1.
Okay.
And that's all you have to do. Let's go ahead and let me put that in. 3, 1. Okay. The next step in graphing a parabola is find points that will determine the shape of the curve. Wow. Kind of hate this question, but that's all right. If I plug in a point, x equal 1, what's the y coordinate? In other words, all I'm going to do is write this equation. y equals minus, and I'm going to plug in 1 for x. What's the answer to that?
-4 plus 1.
Good. That's -3. That's what goes in the y coordinate, is -3. And find the point on this graph that has an x-coordinate of 4. Well, go ahead and plug in 4 for x. What do you get for y?
1. 1 plus 1.
-1 plus 1,
-1 plus 1.
which is 0.
0.
Okay, does this curve open up or down?
Down.
Oh, I really hate the way they do these, but they're doing them kind of backwards. In other words, normally they would say, is that skinnier or wider than the parent function? But now they're giving you another function, and they're asking you whether the original function is skinnier or wider than this new function. What is it? Narrower. In other words, this is 1/4 x squared. This is twice that. Right? In other words, if I compare the original function to the new one they gave us, the original function is twice that. That makes it narrower, the original function. Now it also happens to be reflected, but a reflection doesn't change the width of the curve. The only thing that changes the width of the curve is that coefficient, whether it's greater than 1 or less than 1. And in this case, the top function is twice the coefficient of the bottom function. That makes it narrower. Darren, can you still hear me?
That's better.
I think I lost audio for a minute.
Yeah, you're good.
Okay, cool. You figured out why that top curve was narrower than the bottom one?
Uh-huh.
Okay. Now, this one asks us to find the vertex. Well, the vertex is not affected by either the negative sign or the 1/2 coefficient. The negative sign merely reflects it over the x-axis. That didn't change the vertex. And the 1/2 makes it skinnier than the parent function. But this +4 does change the vertex. So if the original vertex is at 0, 0, where's the new vertex?
Is it 0 plus 4?
Correct, 0, 4. In other words, all I did was move my original parabola up 4 units. These are oddball questions. Not that there's anything wrong with them, it's just they don't teach you transformations. This question, there's only one thing to do. Plug in -2 for x. Well, what do you get when you plug in -2 for x?
So it would be -1/2 multiplied by -4 plus 4.
Now be careful when you square -2. What's -2 squared?
that positive 4 then?
Yeah. In other words, the way I'm going to do this is y equals minus 1/2 times a minus 2 squared plus 4. And then I just solve this, and I do exponentials first. So minus 2 squared is plus 4. So now it's minus 1/2 times 4 plus 4. Minus 1/2 times 4 is minus 2. Plus 4, the answer is 2.
Mm-hmm.
And again, they're just having us substitute a value for x. So I'm going to write y equals minus 1/2 times the 1 squared plus 4. What value does this give us?
So 1/2 plus.
Well, start from there. That's equal to 1.
Yeah.
Times minus 1/2 is minus 1/2 plus 4.
Mm-hmm.
It's equal to 3.5. I could write that as 7/2 or 3.5 or 3.5, various ways. Let's see which answer it likes. Probably 3.5 is going to be fine. No, didn't like that. Let's try 7 divided by 2. Alright. The only problem with these online things is that, boy, you got to get your answer exactly the way they want it. In other words, it didn't like 3.5 or 3.5. It wanted 7 divided by 2. Is this parabola open up or down?
Upward.
Again, boy, they do these backwards. I hate it. Is the upper function wider or narrower than the lower function?
Narrower.
They kind of do these backwards. And the vertex. Where's the vertex going to be? This is actually in Vertex Format. Let's talk about that for a second. Vertex Format is y equals sum a times x minus h squared plus k. Well, notice that that's exactly the format that it's in.
Mm-hmm.
And the vertex is h and k. So h has to be minus 3, k has to be 2. There's your vertex. In other words, we don't have to do anything, any work at all. As long as they're going to give us the quadratic in Vertex Format, the reason it's called Vertex Format is because you're staring at the vertex. It's that and that are the vertex.
Mm-hmm.
So minus, you see why it's minus 3, not plus 3? In other words, it's x minus h is the standard. So the x coordinate has to be minus 3. The y coordinate of the vertex is plus 2. Yeah, all of these are pretty much the same. In other words, they ask you those initial questions and then they give you an x coordinate. They want you to figure out what y is. So what's y here? If x is minus 5.
It would be minus 2.
What's minus 2 squared?
4.
4 times 2
8.
plus 2.
10.
That's what it is. In other words, this part is the easy part here, where you just plug in a value for x. Okay, now what do we got if x is minus 2?
So 1 squared is 1.
Okay.
2 times 1 is 2, plus 2 is 4.
All right. You're going to love math by the time you're done with this.
David.
I'm only partially teasing. There is a precision in math that you have to love. In other words, there's never any subjectivity at all. There's no of this might be correct, it might not be correct. This is either right or wrong. And I can see what you're doing. You're proceeding exactly correct.
All right, so I think I've got this down now.
Okay. Is this open up or down?
This is...
Only thing that matters is whether it's a plus or a minus in front of the x.
This is up. This is upward.
That's the only thing that matters. If it's a negative 1/3, it opens downward. If it's a plus 1/3, it opens up.
Yeah.
All right. So, should we skip over?
Yes.
Okay, how do I do that? Save and end practice?
Yeah.
Save and exit? Or exit without saving?
You can exit without saving. I'm good.
Okay.
All right, so go back to college algebra. And then go to all. And then go to number 8.
Okay. Exponential and logarithmic. Before we start, I need to give you my exponential and logarithmic start. There's only one way to explain logarithms. And all explanations start with this. For example, 8 equals 2 cubed. Okay? Now, you'll notice this expression over here, that's not an algebraic expression. That is an exponential expression. Why? Because the exponent is the variable. In other words, there's a huge difference between 3x squared and 3 to the x power. That's algebraic. This is exponential. You with me?
Mm-hmm.
Exponential expressions cannot be solved by algebra. If I told you that 8 equals 3 to some exponent, I have no way of solving that. Well, I have a way, but it involves logarithms. Okay? I cannot solve this algebraically, not even on a calculator. You can't go to your calculator and come up with the x value on this. Okay? So exponential expressions are in themselves impossible to solve algebraically. So first of all, that's what differentiates an exponential expression from an algebraic one.
Mm-hmm.
Now, every exponential expression has a logarithmic equivalent expression. And you only have to remember one thing. Logs are exponents. Therefore, I can say the log equals x. Now I have to figure out where the b and the y goes. Well, the b is always the base. It goes down there. And the y is only one place left for it. If I were to take this expression on the right and try to make a log expression of it, it would be log base 2 of 8 equals 3. So on the right, those two expressions are identical. They mean the same exact thing. That's what logs are all about. It's taking an exponential expression and turning it into a log expression. Okay, you see where those two are equivalent on the left, and those two are equivalent on the right.
Mm-hmm.
Notice that on the right, my log is equal to 3. Logs are exponents. If you never forget that, then you will not have any problem converting exponential expressions to log expressions. That's where we start logs. Okay, now let's go to your problems. And I don't know how far we'll get today, but let's see. Well, all right, they're not quite into logs yet. They're into adding functions or multiplying functions. Okay, so I started my log explanation a little early. If you're adding two different functions, then it's pretty easy. It's x squared minus 1 plus x plus 1. Remove the parentheses and simplify that. What do you get?
X squared minus...
Well, we got, if I remove the first set of parentheses, I've got that. And if I remove the second set of parentheses, I've got that. Now combine those, simplify that.
So x squared plus x plus...
Ones cancel.
That's it.
That's it. X squared plus x. Now, how do I put this in here? I'm probably going to have to use the keypad, I would think. How do I raise this to a power?
Top left.
Ah, okay. Do I have to put a number in there? I guess I do. So I have to put x, and then top left 2. Okay, now I got it. And plus x. Shift plus x, like that. Okay. So they're going to give us some preliminary stuff. Subtract the two functions, what do you get? In other words, you get x squared minus 1 minus x plus 1. Now notice in this case, when I remove the parentheses, I can't just remove the parentheses. I've got to distribute this negative sign to both terms on the right. If it's a positive sign, you can just remove the parentheses and nothing changes. And I never need the parentheses that are around the first term. In other words, that always becomes that. But the second term becomes minus x minus 1. You see why? In other words, if I distribute that negative sign to both of these terms, I get a minus x minus a 1. Okay? Now that becomes x squared minus x minus 2. And that's our answer. So x keypad squared, what was it, minus x
minus 2.
Minus 2. In other words, adding and subtracting these things is pretty easy. Multiplying isn't even hard. In other words, multiplying is all I'm going to do is x squared minus 1 times x plus 1. Have they taught you the term FOIL?
Doesn't ring a bell.
Okay, that's probably good, because FOIL is a bad thing to teach. Most high schools teach it. FOIL means how you multiply a binomial term times another binomial term. Well, what I prefer is every term by every term. In other words, which works for anything, regardless how many terms it has. So the way I'm going to multiply these two things together is that times that, plus that times that, plus that times that, plus that times that. I call it ET, meaning every term by every term.
Mm-hmm.
Okay, well, what would I get? I would get x cubed as this one,
Mm-hmm.
plus x squared as the second one, minus x as this one, minus 1 as the last one. So there's our answer. X cubed plus x squared minus x minus 1. So x cubed it was plus or minus? Do you remember?
Plus.
Whoops, hold on. I didn't. Plus x squared minus x minus 1, right?
Yeah.
All right, so adding, subtracting, and multiplying is pretty straightforward. There's not a whole lot complicated there. Dividing. Well, this might be a little more complicated, yeah. We've got just about 4 minutes. That's just about enough time for me to explain this to you. Let me take a look at that problem again. Hold on. It's x squared minus 1 divided by x plus 1. So it's x squared minus 1 divided by x plus 1. Well, what you need to know here is that that is the difference of perfect squares, which means it factors into x minus 1 times x plus 1. Difference of perfect squares always factors like this. If I had x squared plus, or excuse me, minus 25, it would factor into x minus 5 times x plus 5. So whenever you have difference of perfect squares, you can always factor it like that. Okay? And since I'm able to factor it like that, and now they want us to divide it by x plus 1, well, I can cancel that with that. My answer is x minus 1. Okay? So I'm not necessarily doing division. What I'm doing is factoring the top and then canceling common factors. When I say canceling, what I really mean is I'm dividing top and bottom by x plus 1. So it's not really, that doesn't go away. It becomes a 1 and that becomes a 1, which gives me the answer x minus 1. And let me go ahead and put that in there. It's actually a terrible problem because that's not actually the correct answer, believe it or not. The correct answer is x minus 1, but x can never be minus 1. So there's a qualifying statement to it. because you cannot divide by 0. And they want us to divide by g of x. Well, if x were minus 1, we'd be dividing by 0. And that's something you cannot do in math. That is the first commandment of math, no matter whose commandment you look at, is thou shalt not divide by 0. So you can never divide by 0, which means this answer isn't quite right. Even though they've counted it as right, I knew they would, the answer really is this, x minus 1 with the provision that x cannot be equal to minus 1. That's really the answer. Because even though we've divided and canceled and come up with this, x minus 1, there's still an original restriction on g of x. Because I'm dividing by g of x, then g of x can never be 0. And what would make g of x 0? An x of minus 1. So even though they give you that as the answer, there's really this qualifier to it. They just don't want to give their attention to that right now. In other words, that's kind of the next level of math above this, is where you have to specify what x can be or what x cannot be. And in this case, x could never be minus 1. Even though it's fine for x to be minus 1 if I'm looking at just the answer. If I look at the answer as x minus 1, well, there's nothing wrong with x being minus 1 there. But the reason it can't be is because the real problem is x squared minus 1 divided by x plus 1. That's the problem. And that's what gives you x cannot be minus 1. That's right off the get-go. Because you cannot divide by 0. Regardless of what else I do in this problem, I can never divide by 0.
Okay.
Okay? Which gives you a final answer of x minus 1 times x plus 1. That's what the top factors into. Divided by x plus 1, well, the x's cancel, so you get this answer, but it doesn't eliminate that restriction. And that's what's difficult with this problem, is that it's called a domain restriction. My domain is not all real numbers here. My domain is all real numbers except x equal minus 1. Maybe they'll address this further as we go forward on this lesson. I don't know. We'll find out. I'm not sure if they will or not, but I wanted to point it out because it's the truth. It's the true math.
Okay.
Okay? So their answer that they accepted here wasn't quite right. Wasn't 100% right. It is x minus 1, but they also have to put the provision that x cannot be minus 1. And it's not because the answer is x minus 1. It's because this denominator cannot be 0. That's why x cannot be minus 1. All right. Let's see. How do I exit this thing and save? Save and end practice?
Yeah.
Let's see. Should I do next first? Yeah. That would be.
Do save and end.
Okay, so we're...
And then just save and exit.
And then... let's log off. Sign in.
You can do that. That's fine.
Okay.
And then just go back to the other tab and log me out of there.
Oh, you got to log out twice. Where's the other log out? It's still under your name?
Yeah.
Okay. That's kind of weird. I'm still not logged out.
Just close it. Just close that.
Okay. Oh, you know, maybe I have to log out of this screen. I'll bet you. I got to log out here. That'll log me out. Yeah, I was in a sub-screen, and that's why it wasn't logging me out. All right.
So I wanted to see if I could schedule some time with you over the weekend.
Sure. Let's look at my weekend here. Easter doesn't work, but Saturday does.
Okay. What would you prefer?
Probably morning. We're going to do it online or in person?
Yeah, we can do it online.
Yeah. How about we do like, what's your preference? You can. My whole day is open except between 10 or 12 and 2.
How about we do a couple of hours? Do you think that would work?
Sure.
Um,
That's really entirely up to you. If you feel like you can maintain
let's do.
focus.
Can we do 2 to 4 maybe?
Sure. Let's do 2 to 4. Yeah.
Did I lose you again?
No, you got me. Can you hear me? My computer's kind of acting up. That's weird. Here, let me try it again. Let me put your name in there first of all. Maybe that'll help. My audio connection says it's lost. My computer's acting up. Can you still hear me, Darren? No, you can't. I'm going to call you.
Hello?
Darren, can you hear me now?
Yeah, I can hear you.
Okay, I lost you there for a second. My audio went bad on my GoToMeeting. Looks like it's been reestablished now. So I got you down from tomorrow from 2 to 4.
Okay.
All right?
Perfect. Appreciate it.
Talk to you then.
Yep. See ya.
Bye-bye.